Hope the screen is visible to you guys.
চলে গেল সব অফ হয়ে
Yeah, the screen is visible, right?
স্টার্ট হয়েছে জাস্ট
Okay, fine. So yesterday, let me just maximize the screen. Okay, Milan, can you mute your mic? Thank you. So yesterday we covered this portion, right? So what can we do if you have multiple structure? So you should take the best resolution and you should look for structure completeness. So if you are looking for wild type, you should take the uh, structure without any mutation, right? So if you are looking for resistance, you want to do study resistance against a particular drug. So if you are looking for that particular resistance for that particular uh, target, then you have to look for that particular resistance, or you can introduce mutation also. Okay, so you can change the mutation, or you can change the particular residue that you want to mutate. Okay, so that is easy. Only I will show you in the practical session. So if you have alternate conformation, you have to check which alternate conformation you have to commit. Okay, so that if there is like 80% occupancy, if you can you know how I have shown you yesterday how to see the alternate conformation for that residues, right? So if you have 80% occupancy, then you can keep the or 80 or 70 or something like that, then you can just keep the conformation that is having higher occupancy. Okay, but it is like in the 50 range, then you have to look for Rotama library. Okay, or otherwise there is no steric classes, right? So it should not bump or come closer to the uh, neighboring atoms, right, or neighboring residues. So there is one way to look at and confirm your alternate conformers. Okay, and if you have, this is not, you won't find this in the literature. Okay, I'm just telling you from our experience. So if you have hollow structure, co-crystallized structure, the most active ligand if you take may give you the best way to screen the ligand databases. Okay, so there are few more uh, you know modification or manipulation or refinement that you need to do before docking with your structure or with your target structure. Okay, let's say if you find missing residues. Okay, so if you find missing residues, what you can do, if the residues that were missing, let's say five residues are missing from like particular stretch of your protein structure or the target structure. Okay, so you can do uh, a loop modeling kind of thing. Okay, so you can put a insert the structure. Okay, otherwise if the missing residue are too many, okay, let's say like 25 30 amino acid residues are missing, then it's better to predict the whole structure. Or in some cases you want to do docking for a target for your target molecule, but the problem is when you search in the PDB database, you don't find the experimental experimental structure. Okay, you are not able to find the experimental or experimentally determined structure of your target protein. So in that case, what you can do is you can predict the structure, right? So you can do by different methods. You can go for homology based protein structure prediction. You can go for fold recognition based, okay, or threading, you can say, or otherwise you can go for ab initio, or AI based structure prediction. Okay, so in this, for example, you can have like modeler is one of the most commonly used software to produce to do homology modeling. Then switch model also is one of the most popular software, and for this threading or fall recognition you can use iTeser. Okay, and for ab initio or AI based you can use AlphaFold. Okay, so I will show you using homology modeling, okay, by implementing this software called modeler and also switch model, and also let's see how AlphaFold prediction does, or uh, you know uh, as compared to the these two homology based modeling methods. Okay, so let's compare the results and see again. So once you have the predicted structure, if you are targeting a particular uh, protein or enzyme, and let's say if the protein structure is not there, you are modeling it, right? So you are using different homology modeling methods. So you can just take AlphaFold if you are confident enough that this is enough, or otherwise you can go for homology based modeling, fold or threading based modeling, or you can take the AI based and compare all the three and take the best structure. Okay, so once you predicted the structure, you can validate the model. Okay, so model validation is one of the important step. So once you validate the model, you can see which model will is having the best I mean the uh, structure. Okay, so some validation methods are there, so I will show you that methods also in the subsequent steps. Okay, so once you have validated or and picked up or satisfied with the model that you have validated, okay, so you can again do what if you want to do targeted docking. Since most of the time if you don't have the target protein, the experimental structure, that means you won't be having the co-crystallized ligand, right? Or if the active site pocket is not reported, or if you don't know the uh, catalytic residues. Okay, let's say this is your noble protein. So what you can do is, if you don't know any information about the active site pocket but still you want to do targeted docking, then you can go for active site prediction. Okay, so you can use various software or tools to do the active site prediction. All right, so if time permits we will cover this also, but I don't think it will be possible today, but tomorrow we'll probably do this active site prediction, and then do docking, and then the uh, image generation of the protein ligand interaction. Okay, why high quality image generation. So let's start with this missing residues. There is one easy way to do. So we can use charm GUI. Okay, this is a web server where you just have to upload or just have to give the name of the PDB ID of your target, PDB ID of your target, then it's very intuitive. You can just read the instruction and go about it, and then predict the missing residues, okay, the structure of the missing residues. Or another way is to use modeler, okay. So when using modeler, we can just take the experimental structure, okay. Let's say we have a missing residue about here, okay. Now you can just use modeler and then model this part of the portion of the missing residue structure, okay. This portion only you can model. So you can just anchor these 2 points. You are not going to change anything in, where in all of the uh, experimental structure protein, but you are going to model this portion. So this kind of modeling is not possible in switch model. So switch model will take the sequence, right? So let's say you have the your protein sequence, okay. You have the experimental structure, but let's say some portion, let's say 10 amino acid residues are missing somewhere here. So you want to model this. So in order to model in switch modeler, you have to give the whole protein sequence, and switch model will take the whole protein sequence and then do a modeling. So when they do the modeling, it will change the conformation of the other uh, protein structure also, other positions, okay, not only this particular position. That's why this only anchoring and doing this particular region only, it's possible in modeler as well as with charm GUI. So I will show you charm GUI for now, and when we do the homology modeling based model structure prediction, we can also cover that this missing residue you know insertion using modeler, okay. Anyway, let me show you this part now, missing residue, how to fix the missing residues, okay. And I forgot to tell you this also. So once you model the particular missing residues, or if you have entire structure predicted, you have to see their structure, okay, if the structure is properly modeled or not. If it is not properly modeled, you can see classes. Some of the residues are coming very close, atoms are very close to another atom, so this is not allowed, okay. So there is classes among these atoms, okay. So you have to remove this kind of classes. So for that you need to do energy minimization, okay. So this also we will do. Let's first see how you can do missing residues or you can construct this missing residues using charm GUI server, okay. So let me just grab that website. Where is that? Okay, so here is charm GUI. Okay, you have to register, okay, and then after registration only you will be able to get all this access, okay, these applications. Let me share the website or the web address here. Okay, once you registered and when you log in, you'll be seeing this interface, okay. So what we need is this second uh, option, okay. When you click to this second option, here you can again see this many features. Okay, so we have to use the third option. Okay, PDB reader and manipulator. Okay, so let's click this third option. Okay, you can use read all this information, and if you want to go in detail you can go to their papers. Okay, this one is their paper, I think. Yes, you go and you can uh, read in detail. For us, let's use our same structure. Okay, so if you look at this structure, you can just keep the PDB ID, or otherwise if you have downloaded structure, then you can navigate to the file and then upload here. Okay, then click next. Here you see the same thing that we have done in the structure, I mean preparation, using Autodoc tool, right? So removed we removed everything except for the receptor and the ligand. But for now, what we are our objective is to find missing residues. If any missing residues are there, we have to add what were the residues that were missing, right? So for now, let's just uncheck all this. Okay, unwanted chains, you can say this as unwanted chains because we are not using this for preparing the receptor. Okay, so I am taking only chain A. So this is chain A is starting from residue number 4, then it last residue is 542, right? And then you click next. So remember, or if you can understand this, I am checking this protein, this one only, because this is chain A, and since the our protein structure is a homodimer, I can just take one chain, right? Only one chain or only the one monomer, and then go ahead with that. Okay, all other things that are shown here, it's not required for fixing the protein structure, right? So that's why I'm unselected everything. Then go to next. So this will take some time. So in the meantime, let me show you this. Okay, so we have to do protein structure prediction. So when we have to do this protein structure prediction, when you don't have the experimental structure of your target protein. Okay, so you have found out that a particular target is involved in a disease condition, right? So it was, some kind of reports are there, or you have done some studies, and it is found as that by manipulating, or by altering the function of that particular target protein, you might be able to reverse the disease condition. But when you search or when you do a research, you are not able to find the experimental structure of that target protein. So in that case, you have to predict the structure of your target protein, right? So there are many methods. So using AlphaFold, because of this AlphaFold, I think Jumper was the one, right? He got a, Nobel Prize for developing AlphaFold. Okay, so you can use different methods. You can use homology based, you can use threading based, or you can use AI based or ab initio based modeling methods. Okay, so I'm going to show you here using modeler, and then switch model, and then alpha folds. Okay, So this is how the workflow works. You have the sequence of your target protein. So you have the sequence, you know that this particular protein is involved in particular disease, but you don't have the experimental structure, but still you have the sequence of that protein. So you can take the sequence of the protein, you can search in a structured database, experimentally determined structured database. Let's say in PDB you can search, you can find similar uh, sequence. Okay, when you search in a database, it will be containing the sequence as well as the experimentally determined structure of that sequence, right? So that means for this uh, protein structure of that sequence. So you are going to search in the database, but you will be searching sequence to sequence, and once if you find that the sequence are similar or homologous, then the idea is if the sequence are similar or homologous, their structure must be also similar, right? So those which are having high similarity or identity, you can take those sequences and their corresponding structure. The corresponding structure is called a template structure, where you will be using this template structure to model the protein of your target. Okay, so the target is your protein is called the target sequence, and the sequence or the structure that you will be getting while searching in this experimental database. Okay, experimentally determine structure database, it will be called as the template. Okay, from the template you are going to model the protein. So the predicted protein will be again validated using various methods. Okay, so this is the workflow. So switch model also follow the same thing because it is homology based. ITESR, they have different way of different steps, and again this AlphaFold also have um, a different way to build the model. Okay, so for AlphaFolds, the way they have predicted, it's kind of complicated, and if you know if I say sincerely, then I'm not able to get properly how they are doing that. Okay, it's a little bit complex, and you need to have uh, deep understanding about this AI or machine learning based algorithms. Okay, so let's see how this CharmGeo has done. So you see, after going to the previous the steps, the first step, you will be getting this kind of interface. So here you can see the model has missing residues, right? So from this to this region it has missing residues, that is from 259 to 264. Okay, and from 495 to 497. Okay, these are somewhat, you know 59, 60, like 6 7 amino acid residues are missing in these regions. Okay, but these are not in the active site pocket, but still if you are going to do after docking molecular dynamics simulation or any other study, and if you want to see changes in the structure when the your inhibitor binds, and if you want to compare with your reference drug molecule, so it's always ideal to add the missing residues. Okay, but it is compulsory to model the missing residues if it is seen in the active site pocket. Okay, so these are C N terminal and C terminal, that's why they have not by default selected, because in a C and N terminal it is somewhat allowed to have this missing residue kind of thing. Okay, so you can select this. So when you select this, it will model the residues, all these residues, and these are all protonations that disulfide bond if it is there, so leave it as it is. Okay, then you can go to the next step. So our important our main focus is here. Okay, so you have to check this and select according to your study. Okay, if you don't want to model the N or C terminal, that's okay, but if it is N and C terminal are important, you can just check the regions and then you can go ahead with the next step. So again, it will take some time, so let it run. So let me come back here. So let's start with modeler. Okay, so modeler, uh, it's sometime, it is like, it kind of, it's kind of now obsolete, but not exactly obsolete, because many of the thing that manipulation of the alignment, and if you understand your active side pocket clearly, and if you have a very close homolog, or you can say high identical uh, template, then using homology modeling, using modeler, okay, or otherwise switch model can give you similar kind of, or even equally good model like the alpha folds. Okay, so it depends on your study, so it's always good to have knowledge about homology modeling using modeler. So these are switch model, this is automated one. Okay, so you cannot do many manipulation, but in the case of modeler, this is manual, and it has to be done through command line. Okay, so but the good thing about this is you can manipulate all the steps if you understand what you are doing. Okay, and then you can get a very good results. All right, so you have to, okay, it is done. Okay, so this is the uh, final structure. Okay, so if you download this, you will be having the missing residue fixed. Okay, so let me check. Otherwise I can just open the, yeah. Yeah, let me just, okay, it's starting from beginning. Anyways, I wanted to show you where were the missing residues. Okay, in our case, in our protein structure, the original structure, it started from residue number 4. Okay, but see, it's starting from residue number 2. Okay, so that means it has inserted uh, the residues, and also if you go down, it is now 4. Okay, let me just see. All right, so missing residue was 259 to 264 was missing. Okay, in our original PDB structure. So if you go to, what was that, 259, right? 259. So 259 should be here after inserting the missing residue, using fixing the missing, yeah. So 259 is there, right? 259 is there till 264. Okay, yeah, it's all there. So it has fixed the missing residue problem, and now you can use this structure for further study. Okay, so imagine this is in the active site pocket, then you have to model this particular stretch of the missing residue. Okay, so this is how you can do using Charm GUI. So this is the easy part, but if you do in modular, it's somewhat difficult. Okay. All right, so let me just go to modular. So now you can just download this. If you are using Windows 64-bit operating system, you can use this link to download and install it. So when you install it, you'll be getting a licensed to enter a license key. So you can enter this. Okay, you can enter this license key. Okay, that I have messaged you just now. I've sent you in the WhatsApp group also. Okay, so when you install it, you will be getting a this command prompt kind of thing. Okay, this is not CMD. So when you type modular, you'll be getting this command prompt using modular. Okay, so just open this, and now you see this is modular version number 10.5. So if you want to see if your this tool is properly installed, you can type mod then 10.5. Okay, uh, or if you are in the you are install newer version or older version, you can see that you have to type this version. Okay, so in this case it is mod 10.5. When you press enter, something similar to this message should be there. Okay, if you have properly installed. Guys, you're following, right? You are able to follow, or am I confusing you? Okay, fine. So now we have installed the modular software, open it, and we are going to start using modular to build the protein structure. Okay, so let's take a real example. So you go to UniProt. So UniProt is a database where it stores about all the available information about proteins, okay, or enzymes. So let's take an example of a protein or enzyme called pepsipin. Okay, this is a cysteine protease in the organism named Pepsia bejigimina. Okay, this is a protozoa. Okay, if you scroll down, and this is the amino acid residues, okay, or the sequence of that protein. Okay, so let's model this protein. If you go to PDB database, you won't be able to find the structure of this experimental structure of this protein, and here also you can see. Okay, so in UniProt you have this structure information, only alpha fold structure is there, and again you see it's not properly modeled. Okay, this part is not modeled properly. Even alpha fold cannot do the proper modeling of this part. Okay, so there's some reason for that. All right, so we'll be using this sequence for generating the 3D structure of this protein. Okay, but before that, let's go to this tutorial. Okay, let's go for this basic modeling part, and here you can read. Okay, but I will go through this uh, very quickly. So this is the target sequence. And for modeling the structure in modeler, you need this format. Okay, this is a PIR format. Okay, this is called a PIR format, and you need to keep the same format, okay, as your as defined here itself. Okay, so what we can do is we can just copy this. Let's go to that, or let's create a working folder for homology modeling, right? Homology mod modeling, right? And let's create, or let's open a new file here, paste it there. Okay, so this is saying that it's a protein, and this is the name of the protein. Okay, so let's keep the name change here as Bepsipen. So just to recap, what we are doing right now is we are trying to, use the same format that was given in the tutorial. Okay, so this is a PIR format, so we cannot mess up this particular format that they have given. If you missed any of this colon or something, it will throw error when you try to run the subsequent steps. Okay, that's why I'm just copying the whole this PIR format that was given in the tutorial, and just we are changing the name according to our target. Okay, name in the sequence. So this defines the name of the protein, so we are going to name this as Bepsipen, right? And then this sequence also, this will be the sequence name. Let's keep this as also as Bepsipen, right? And then let's change this whole sequence to our sequence. Okay, so if you go here and see, this is the sequence of Bepsipen. Okay, amino acid sequence. So let's do this download. Let's copy this and then paste it here. Right, so we have converted the PIR format that was given as an example in the tutorial to our target sequence in the PIR format. Okay, so this star is also important. Okay, if you forgot to keep this star, again it will give you error. Okay, so we are just keeping everything, but we are just changing the name of our uh, target protein and the sequence of our target protein. Okay, just replacing the target names and the sequence. So let's save this. Go to file, do save as, and go to our working folder, and then where is that homology modeling, right? Let's change this save as type to all and save this as beb c pen. Okay, and the extension should be .ali. It is a PIR format, but the extension is .ali. Okay, and then click save. So you have the target protein properly processed in PIR format with .ali extension. Okay, so here we have a first process that we are doing here, and then let's go about the second process. Where is that? Yeah, the next thing is to select a template. Okay, so if you go back to our this homology modeling workflow, we are supposed to select a template, okay, from a experimental structure database. So let me explain this. Okay, so if you are not able to follow, just let me know. Okay, I'll just try to repeat it, or I'll try to simplify more. Okay, so you have the target sequence. Okay, you got it from UniProt, right? Got it from UniProt. You have the target sequence. Now you want to build this uh, 3D structure of this particular target, right? So from this target itself or the sequence itself, you cannot build the structure using homology modeling. So the name itself is homology, means it should be, you should have something homologous protein structure to build the model. Okay, so what you can do is you can take this sequence and search in the structure database. What is this structure database? They have already experimentally determined structure in this database. So for example, we have PDB, right? In PDB, all the experimentally determined structure are stored, right? For this experimentally determined structure, they also have sequence, right? So for this, you have sequences. All these sequences have corresponding experimental structure. So what do you going to do is you're going to align your target, okay, and then see if your target has similarity with your sequences that are present in the database. So if you have high sequence similarity or identity, you can pick up those sequences and take it as a template for modeling. But there are some criteria that you have to follow. Okay, so there is something called sequenced identity, or sequence similarity. Okay, so we are looking for sequence identity in this case for selecting the template structure. Sequence identity means you have histidine here, you have histidine here. Okay, you have tryptophan here, you have tryptophan here. Tryptophan is what? Y, I think, huh? Tryptophan is W, I guess. Y is tyrosine, right? So these are identical residues, right? But you say you have tryptophan here, this is tyrosine here, these are similar, okay? Their properties are similar, they are both aromatic, right? So we are not looking for similarity in case of searching templates for this target, okay? Target sequence. So you will be looking for how much sequence identity is there when you align this target sequence with your database sequence. Okay, so if the sequence identity is more than 30%, okay, then you can say it's a good kind of alignment, or not that good, but it is okay kind of alignment, and you can build a model from this. Okay, but the quality of model won't be that great. Okay, but it's above 50%, okay, then you can take this confidently and then you can build a model. If it is less than 30%, then something we call it as twilight zone. Okay, and then the quality of the model may not be good, but if you don't have anything else, you can just take this alignment and take the template and build the model. Okay, but you have to be very careful. But if it is more than 50 or 50 to 60 or above 70 80, then you can just take the template and build the model confidently. But the but you have to again have a concept called coverage. Okay, so what is this coverage means? So when you are searching this particular uh, sequence of your target against the database sequences, okay, you may get, let's take an example, okay, for this first sequence. This is your target and this is your database sequence. This is your target sequence, this is your database sequence, right? So it's aligning. Okay, so it's aligning here from here to here. Okay, and your sequenced identity, it's let's say 80%. Okay, that means very good alignment. But the problem here is, see, you have a coverage of around, let's say 60%. Okay, so this is the target sequence and this is your database sequence. So if it is aligning from here for the first uh, part from here to here for 60%, means you will be able to build the model like 60% of the structure from this particular template. Okay, from starting and terminal to somewhere around here. Okay, that means you will get the structure of this particular uh, region. But for this particular region, mm, uh, you won't be able to get the template, okay, or any reference, uh, structural uh, reference for to build the model. Okay, let's say that the active site is present here. Okay, so if you are going to do docking and the active site is present here, and if you are building the model, because you are just getting 80% sequence identity, but the coverage is also good. Let's say 60% is considered to be, good only. But even if this coverage is also having 60%, but you know you are building a model, but the active site is not present in your final model that you are going to build, right? So what is the point? Your objective got defeated, right? So what you can do is you can just see other templates if it is present. So this is the first template. You can look for second template. So if the second template, even though it has, let's say, 40% sequence identity, okay, 40% sequence identity, but still it is able to cover the active site pocket. And even if it has lesser also sequence coverage, okay, 30%, let's say, still it's better to take this, or it's logical to take this particular template to build the model, exclude all this region, build only this part of the protein, okay, or the sequence, right? So that you are able to get the active site pocket, and then you can use this model for doing, virtual screening or molecular docking. Make sense? Yes, guys, following, right? So yeah, so this is why I'm telling you that homology modeling or modeler, though it's kind of technique is very old, but still it is very useful, because when you give the whole structure sequence to AlphaFold, it will just build the model. Okay, you won't be able to see, you cannot manipulate anything. So in this case, we can remove or adjust the alignment so that we can get, if you are very rigorously studying or researching your target protein, then we can manipulate so many things. Okay, but for now you just learn the basics. Okay, and whenever required you can look at a tutorial. Once you learn the basics, it will be easy for to do the advanced or from the tutorial. Okay, so you can build this model, right? And you can use this particular structure. So once you have this, you can do a proper alignment. Okay, so in this searching, you are just aligning using the sequence information. So another alignment we have to do in modular. Okay, this is using some blast search or something. Okay, so but after getting the particular template or after selecting the particular template, you can do second alignment. Okay, you can call this as second alignment, or you can call this as a uh, alignment in the uh, homology modeling step. Okay, so proper alignment. So in this second alignment, using the template, you will be uh, using the secondary structure or structural information when you do the alignment. Okay, so now after doing this, some kind of structural information will be added, not only the sequence alignment, but information or some kind of parameter from the structure will be derived, and you will be performing that alignment. So modeler will be used to do the alignment, and once you have the alignment ready, you can start generating the model. Okay, final model. So let's
Hello,
do
sir.
this. Yes, yes.
Can you repeat the second alignment step again?
So, okay, I'll show you in the practical itself. Okay, that will be more,
Okay, sir.
easier to understand.
Okay, sir.
So start. Let's use this particular sequence, and then let's start doing the search for our template. Okay. So today it may take additional 1 hour or something. Okay. So be patient. So let's cover this up. Okay. And if I'm not able to cover up the missing residue model building using modular, I'll be making a video and then sending you. Okay, but for this homology modeling and then model validation, we have to cover this. Okay, so please stay with me till then. So let's do blast p. Okay, so if you go to blast p, it should start from this greater than sign. So FASTA format you have to enter. Okay, so just give this name as Pepsi pen, and then the next line it will take as the sequence. Okay, okay. So important thing is here in the database you have to select protein data bank. Okay, so we are looking for sequences that has protein structure, right? So all the sequences stored in the protein data bank will have corresponding 3D structure. Okay, so select this database and then start doing blast. All right, so these are the results that we are getting. Okay, so if you go to this graphics summary, anyway, let's see this uh, parameters first. So it has 44% sequence coverage. Okay, so forget about all these things. So what is important is our sequence coverage and then sequence identity. Okay, so this is sequence identity, it has 40%, right? And then sequence coverage is also 44%. If you want to see this graphically, so you see sequence coverage, some other structure has 70%, right? And if you see, yeah, I think this is, yeah, some, yeah, this one is having 41, 42. But how how should we select the template? Okay, so two criteria we understood from our previous theory, right? Previous explanation that I did. So you can go for this sequence coverage, it is 70%, but still if you go for the sequence identity is 33% only. But if you want to go for this higher sequence identity, okay, 41, let's say, the sequence coverage is less. So let's understand one thing. Let's go to this graphic summary, right? So the first sequence, or the first database sequence is having this is our whole query. Okay, it started from 1 till 450, but the first one is having sequence coverage from the middle of our uh, query, or the query sequence, let's say about 250 amino acid residue. From there it is having sequence coverage, right? So the second one also, and this one is the fourth or fifth one, is having sequence coverage of much more. Okay, but the sequence identity become less, 33% something. So before doing any homology modeling, any molecular docking work, you need to research, or you need to study what you are trying to build or what you are trying to study. Okay, so in this case, if you look at this particular uh, protein, that is the enzyme, that is the bepsipen. Okay, so if you go back here in UniProt, I'm just showing you here, but if you are really doing a research and if you want to go for publication or any other further experimental work, you have to be very careful. Okay, so there are two domains. Okay, so the first domain is cathepsin propeptide inhibitor domain. Okay, this is not we want. So papain is superfamily. Okay, so under this you have this cysteine protease family. Okay, protein family. So we are looking for this particular domain. Okay, so this particular domain start from residue number 244 to 452. Okay, so somewhere from here 242 to 452 something. Okay, so that means if you remove the sequences of I mean before this, right, before this particular domain, you may be getting your sequence coverage high as well as sequence identity. Okay, I mean sequence identity will be remain the same, but the sequence coverage will become high. So our aim is, or objective is, to do molecular docking, and the active site pocket, or uh, the region where they are going to do some proteolytic activity, will be in this particular domain, right? So we will be interested in modeling this portion, and we can leave out this particular region. Okay, so what we can do now is we can just copy this, paste it here. Let's select till how many, 240 something, right? So I'm just, yeah, I'll just delete this portion and then just use this remaining sequence and start the search again. Okay, same thing. You have to change this to protein data bank and do blast. I hope you are not confused. Okay, why we are removing those particular region? Because when we did the blast search, we are not able to find structure which can cover the whole protein structure, but many of the proteins or the sequences from the database, it's able to cover the domain that we are interested in. So we can just take that portion of the domain where active site or the active site pocket must be there. Okay, because we are interested in doing molecular docking. Okay, so we can just build the model using that particular portion. Even AlphaFold is not able to predict the whole protein structure, right? So this must be the end terminal where the missing most of the uh, sequences or the sequence residue was not able to find the template. Okay, so now you see the sequence identity the same, but sequence coverage has risen. Okay, so it's now 90% of the sequence has been covered. And if you go to the graphical summary, you can see this sequence is completely covering the target sequence. And if you see the alignment, okay, you can see plus means sequence similarity, and if you're writing the same amino acid residues in the middle, that means you have sequence identity. Okay, and these are gaps. Okay, so now from here also, okay, there are some plant protein also. Okay, plant enzyme. So you should be also careful to select, even though if you are having query coverage that much, sequence identity that much, but I would prefer the template to be, you know, somewhat evolutionarily related organism. Okay, so Plasmodium falciparum means it's a, I think, tropozoite or something, right? I don't know. This is like microorganism, but similar organism for our this particular. Let me just see. Okay, Plasmodium. It's a malarial parasite, right? Protozoan. Okay, so yeah, correct. Protozoan only, and our target protein is also a protozoan or protozoa. So I will be, selecting those protein from this source organism which is close related to our target protein, okay, or target enzyme. So I would prefer to select the this particular organism rather than a plant-based uh, source. Okay, even in the plant also you have similar kind of protein folds, so the similar enzymes are there, similar proteases are also there. Okay, but it's always better to select which is organism source which are closely related to your target. Anyway, so let's select this one. Okay, 6JW9 as our template. Okay, so we just need to know which template to select using all the criteria that we have listed before. And then once you have selected the target or the template, you can go to PDB, and here you paste the PDB ID. Okay, this is the section, is this first part is the PDB ID, and A means chain A. Okay, you are aligning with chain A of this particular PDB ID. So you go to this PDB database, type the PDB ID and search. Okay, so let's download this. So if you want to download the PDB file, you have to go to this PDB format. Let's go download it, copy the file, and let's paste it in the working folder. Okay, so you got these two files now. uh, Essentially you have selected the template now. So the next thing is alignment. Okay, go back to the tutorial. Okay, so this is the same step that we have done, but they are writing a different program to select the target protein. That's okay, you can follow this what they are doing also, but to make more sense, you can use uh, the PDB or the blast P, choosing the PDB database and then searching for that particular template and looking for the sequence identity as well as sequence coverage. And the sequence coverage where it is covering, you should be able to cover your particular domain that you are interested in. Okay, if it is covering the whole structure, then it's fine, you can just take it. And if it is present with different organisms, you should look for the organism source which is closest to your target protein or the enzyme. Okay, so the next thing is this alignment. Okay, so when we did this blast search, we are just doing a alignment based on the sequences. So database sequences present in the uh, particular PDB database. Okay, now when you are doing blast search, you are not looking for the or taking the information about the structural properties to do the alignment. It's just looking for the sequence based alignment. Once you get the sequence proper sequence alignment, we are just looking for this particular accession number or the template ID or PDB ID, and just you are taking this as a template. But there is again another alignment that we have to do. So this is the aligning the target and the template. Okay, in this case we are going to use modeler, and modeler uses some kind of uh, you know see so some kind of structural information. Okay, so in the solvent exposed region or curved region or outside a secondary structural element, they are going to use some kind of penalty function to align. Okay, so this information or these parameters were not used in the simple alignment that we have done using blast. So we have to do a proper alignment again using modeler. Okay, so for doing the alignment uh, using the uh, target and a template, we need this code. Okay, so this is a Python code, so you just need to copy this. I'll explain. Okay, don't worry. Paste it in a new file, and now you have to change this information. Okay, You don't need to change the code, you just need to change the name according to your files, okay, or according to your target that you are doing. So for us it is pepsipen dot ali. This is our target and this is our template, right? So here this is their template structure and it is looking for the chain A, first position of the chain A till the last position of the chain A. Okay, so for us we have to change this to, let me copy this and paste it here. For us also we need the chain A. Okay, so let's not change anything here. Again you are you have to change this, okay, to the PDB ID or the PDB code, right? Same thing here. And then this, for this we need the target name, right? Target name dot ali and target code. Okay, let's keep the default parameter and then let's change this. Okay, this is the output. Okay, you can give any name, but let's keep the same format that they are doing. All right, so you'll get a two files, one in PIR format, this will be used for in the next run, and one is in PAP extension. This is, you know, human readable and it is easy to see the alignment. Okay, so we have to save this in Python format. Okay, so let's change this to all files and let's say this is, you know, align.py. You can give any name, so I'm giving this for short for alignment, align.py. So the Python uh, file should be in py extension. Okay, save this. So let's run this. Okay, to run this, the same thing that we were doing, the same thing you have to follow. So you are in D drive, all the files are in D drive, and your Python path or the modular path is in C drive. So let's change the drive and the path, right? So to change the drive, just type the drive name and then colon, press enter and do cd, that is change directory, and the space, copy the address of your working folder and then paste it here and press enter. So now you are in the same path, right? So do dir. Okay, now it will list all the files that are present here, right? Done. So we have this Python code align.py. We have properly formatted, we have changed the names of our target and the template. Now let's run this. Okay, to run this you have to type mode dot 10.5, your version of your modular, and then just type the name of the script and press enter. Okay, I did something wrong here. 10 point, okay, I kept dot here, that's why mode 10.5 should be like this, and then press enter. So it's running. So it has produced two files. Okay, if you open this, okay, there are too many gaps here. Dashes are the gaps. Asterisk means identical. Okay, so these are similar residues. Anyway, let's build this structure. It won't be that much accurate. Okay, but the thing is, uh, let me just show you the. Just 1 second, okay? So this is the work that we done long time back. Need to find from where did we take the so pro domain here we have taken identified based on the earlier report. So 217 amino acid residue only we took. Okay, so this is why it is always important to first research about your protein structure or I mean the target protein, then go ahead with the docking or homology modeling or anything else. Okay, so if you go to this particular reference, the proper experimental study must be there where the prod or active domain it start from this particular I mean it contains only this particular residue. That means what we can do is we can select, let me just copy this, select from the N and just select what was that, 217, right? 27. Copy. So now we have changed the uh, target protein sequence. Okay, save this. Why I'm doing this is because where is that? Yeah. If you open this, you can see so many gaps are present here. See. Okay, this is because we are taking the whole protein structure, whole protein sequence. That's why. Okay, let's rerun this. Otherwise, it won't model properly. Okay, so this were the sequenced where I mean the template cannot cover this particular portion of the sequence or of our target sequence. Okay, so let's rerun the alignment again. Let's delete this. This again. go to new alignment files, you open and see. All right, this is better now. So at the end terminal, you don't have this, you have this missing residue. That's okay. I mean, yeah, here also you have some gaps, but that is fine. Later on, you can do loop modeling or refinement, okay? But anyways, we are going to model this properly now. Are you following? Why I deleted the sequence, target sequence again, and did the alignment again? Guys, anyone can respond. So everyone got confused. All right, let me continue. Okay, so you go to alignment files. Now, the next step is to build the model. So let me just get it. So for them also, in their example, this is the alignment that we have just seen. And the next step is to build the model. Okay. So again, we have to create this script. Okay. Paste it here. And then here is the alignment file name. So in our case, what was that? This one. Okay. So let's just copy this name, paste it here, replace it, and then replace the name of the file. Ours is Pepsi pen, right? Here, this is Pepsi pen, and our protein ID is this one. Okay, chain A. That's it. So some scoring function are there to access the protein model. Okay, and then it start from one model to 5. If you change this to 100, it will create 100 models. Okay, so let's just skip 5, and then let's save this. We'll be saving this as with the py extension. Let's give the name as model.py. Okay, save it. I think it's okay now. Change the name of our protein target and template alignment file. Protein file is here, the structure file is here, the target sequence name is here. Okay, that's it. Starting 5 here. Okay, so you can run this same way. It is mode 10.5 and then say model.py. Press enter. So it's running. It started to build the first model. Second, we have given 5, so it will produce 5 models of the same target protein. Okay, so yeah, it's done now. So we have 1, 2, 3, 4, 5 models. So out of these models, which one will be the best? Or if your the model that you have generated, it is acceptable for docking or not. So let's see, or let's validate the model. Let's start with the first one. Okay, so for there are various ways to do model validation. The very important one is using Ramachandran plot. Okay, so in Ramachandran plot you will be looking for psi-phi angles of each of the residues present, and you will have a plot where you will be finding a region where you are favored, okay, for the psi-phi angles, favored psi-phi angles. So in the favored psi-phi angles you won't have any classes between the residues, okay, atoms of the residues. And when there will be again some kind of disallowed region, so in the disallowed region if residues are present, that means the psi-phi angles of that particular residues is not proper. Okay, that means when you are modeling the protein, or if your region of that particular residues in the disallowed region, they may be having very flexible region. Okay, so let's calculate this Ramachandran plot. You can go for this particular address. Okay, I'll just copy this and paste. Go to this web address. Okay, let's select our file. So here, and after this homology modeling, let's check for the first model. Click open and then click run. So in this web server you will have this application called ProCheck. So it will check the stereochemical quantity of the protein. So Ramachandran plot is one of the application that is present in ProCheck. Okay, so let's start this particular program and see if our structure is, you know, acceptable or not. So another way to do validation is you can use a server known as Q min server. Okay, so in this Q min server they have various ways to score it. So they are storing the uh, some properties of the experimental structure, and then those properties they are comparing with the predicted one. So your predicted structure will also be calculated the same properties, and they will compare and see if your structure is closely related to the properties, or if your uh, predicted structure properties have the similar kind of values with the experimental one. Okay, so from the databases of experimental structure they will calculate a set of properties derived from that experimental structure. The same thing, you will be calculating the same properties from your predicted structure, and they can compare it and see if your uh, predicted structure has similar kind of properties or not. So if it is similar, that means your structure, predicted structure may exist in, you know, uh, uh, real in real, you know, uh, uh, world scenario. Otherwise, if it is very much deviated from your experimentally calculated properties, then probably your structure is wrong and it may not exist in nature. Okay, so you can use qmin server, and these are various methods. Let's try with the first one. So you can just upload your model and then press submit. Okay, so it's still running. This one is also running. Everyone with me, or It's all dark now. Guys, please respond. On. Okay, for this you see, so here uh, there is some score they have given, okay? Closer to 1, better is the model. So 0.66 means the model is that not, it's not that good, okay? It's kind of average model. And this color scheme, if you see, blue means it is, they are very confident in this particular region where it is blue, and then orange means it is poorly model, okay, regions. So you need to refine this model, okay. And here if you see, this is from range from 0 to 1, the same thing. So the properties that you have calculated, and the for this particular model, and the properties from the experimental structure, okay, you are comparing it. So for each of the residues you are also getting the scores for that particular properties, and you are saying that from this region the score are very bad, okay, this orange color regions. So you need to do refinement around these regions, okay. The blue ones are good ones, okay. So you have very confident structure model here. So next thing is to do energy minimization, okay. So when you do energy minimization, this may come down, okay, or this score may come up, okay. More than 0.7 something is considered to be good. You can go for docking in that case. Okay, so project also done. You can go to this result option. It's taking time. So let me show you how to minimize this. You can go for a server name as Galaxy uh, refinement server. Galaxy refine server, okay. So if you go to this server, you can just upload your protein, okay, and then submit. But you have to keep your email address here because it takes time. It takes around 1 hour, something like that. But already I have done refinement, so I have a structure form. I already have a structure refined using Galaxy, okay. So let me just upload that and see how the validation changes. Galaxy refine, where is that? Why? So let me get that. Galaxy. Yeah. So here I've done the for Pepsi Pen. I have done the refinement using Galaxy. You just have to submit the file to Galaxy and they will give you the refined structure. Okay. So if you click here, this is the structure, and they have given the Ramchandran plot also here. So in the most favored region, it should be more than 90%. So one of the structure is having 97%. So previously without the refinement initial model it was having 87% of the most favored region. It's 87%. Now after refinement it's showing 97%. Okay, let me just download this model number 5. Okay, and then upload in this. So it was having our previous before refinement it was having 0.6x, right? So if you go back and then go to the downloaded folder, model number 5, right? So that we have downloaded just now, and then click submit. And here also Ramchandran plot, you see it is having 81%, okay, in the most favored region. So this is how you can see the Ramchandran plot. Red colored contour maps region are the ones which are favored. Okay, that means the sci-fi angle are such that there are no steric classes. These are uh, as additionally allowed region. Okay, so in this the regions are some kind of classes kind of thing may be there, but they are allowed. Okay, and they are not frequently seen in the uh, such kind of conformation. So but they are still allowed. But in the these are the white regions are the disallowed region. So if the residues are in the disallowed region, that means you have some problem with the conformation or the model that you have generated for this particular residues. So if you want to you know the model to be acceptable for molecular docking and other studies, it should be above 90% of the residue should be in the favored region. Okay, more than 90%. So let's go back again, go to this, and then select the refined model, minimized model, and then run this again. Let's see if the Ramchandran plot got improved or not. Here also, if you go see, it got changed to 0.71. It was previously 0.66. So above 7 is okay for doing molecular docking. Okay, it's taking time. So let me just quickly show you switch model. Okay, so if you go to switch model and click start modeling, you can paste the sequence here. So let's take the same sequence that we have. Where is that here? This one. Open this in any text editor. Copy this sequence. Paste it here. Okay. And then just go for directly to build model. Okay. So again, it's going to take some time. Let it run. So for alpha fold, you have to go to this alpha fold 3, then server. Okay. So this is the first one, is the one that you can do modeling. So he will ask you to make a account. Okay, so I have already created an account, that's why it's showing here directly in this interface. for me. So now you can paste the eh, your sequence here. So the same sequence from there, from our same sequence, I can paste it here. Okay, and then so you have to make this proper. Okay, and then I can say continue. Okay, but the for alpha phone it allows some restriction, so you can run 20 times like that. So I have already run one job, so 19 are remaining for me now. So this is the uh, structure after running that. Okay, so after running you will be getting this kind of information. Okay, this tick mark. Okay, that means your structure prediction has been already completed. When you click this, you'll be getting this kind of structure. Okay, so this is the score according to AlphaFold. So blue means very confident that these are the uh, correct or accurate structure. Okay, so yellow means very low confidence and orange means worst. Okay, so this is how AlphaFold predicted, and you can go for download option here. So all the structure will be downloaded in the zip file. Again, when you open this zip file to download, so AlphaFold, yeah, here. See, you have this CIF format. Okay, the same thing only. This is like PDB only, but the format is different. So if you want to convert this in PDB, you can use this Maestro. Okay, so let me just show you how to do that. So you can open file, then import structure. Yeah, downloads, then the downloaded file, and then just select one of the CIF extension. Let's select the first one, open this. It is open here, and then if you want the PDB format, you can just go to export structure. Okay, and then you can navigate to your folder, D drive, this one, homology modeling. I can give this as alpha ph here, right? Dot pdb, right? And choose export. So if you go back to our working folder, we must be having alpha folder here, right? And then if you go back again and see, okay, this is after minimization. Okay, let's see the changes. The Ramchandran plot, it was before the minimization, it was having, using homology modeling, using modeler, it was having around 81% in the most favored region. Okay, again it's taking time, so let it be. So this is after refinement of the model that was predicted by modeler. Okay, so let's go back and use AlphaFold and see how AlphaFold performs. Okay, D drive, here, homology modeling, AlphaFold, open, and then submit. Okay, so Ramchandran plot. Okay, most I think this is glycine. Okay, glycine is okay in the this particular disallowed region. Okay, so 90% of the favored molecule are in the favored region, so it has improved like 8%, something like that, right? 9%. So now we can use this for further studies. Okay, so this is how you can refine the model, check, validate the model again, and then proceed with your other studies. So this is the AlphaFold model. So AlphaFold model has the highest Q-mean score, global score. It is having 0.75. So this is without refinement. Okay. So if we go for refinement again, maybe AlphaFold model will perform better also. So now you can do refinement for this also, and then uh, validate again to see if the improvement is there or not. Okay, so if it is improvement is there, then you can use this AlphaFold model, the refined one, to do molecular docking studies. All right, so here we have predicted the 3D structure. If the 3D structure is not available for your target protein, we have compared with different modeling methods, and I think still, yeah, for this also it's done. Switch modeler. So in switch modeler and AlphaFold, you just need to give the sequence information. Then you have just click the predict button, and then it will do the prediction automatically. And switch model also is giving like Q min. So switch model is already integrated in the switch model generation results. Okay, so you don't need to separately go for this Q min prediction. Okay, so Q min, this global score is about 0.75 for switch model prediction. Okay, this is also good, right? So a Ramachandran plot we have not done, so you can download this and do the Ramachandran plot also for this. Okay, guys, tomorrow we'll be doing uh, binding site prediction, and after binding site predicting the binding site, we'll go for molecular docking for one single molecule against the target. Okay, so let's do binding site prediction for the same protein. Okay, so let's predict the binding site and see where how it performs in the docking using the same predicted model tomorrow. Okay, so only two of you are there, huh? Thank you for your patience. Okay, any issue, any question you have? Everyone slept over. Okay, okay, John. We'll see tomorrow again. So tomorrow will the last session, but I'll repeat again. If you have problems, let me know. We can connect and we can solve the issue. Okay. All right. I'll send you all the files that we have done today. And
Sir,
yeah.
sir, send the video, recorded video for all the sessions, sir. I could not understand. Only few things I could understand, especially in the previous classes, first two classes. So after that,
Okay.
it is
Okay.
very, very difficult to understand, sir, because I don't have any basic ideas regarding about this molecular docking, sir.
Okay. Fine. Fine.
So,
No problem.
okay.
So I have already sent the videos. So you are not getting the videos. I have sent in the email.
No, sir, only one video I find in the email, sir. That's the fourth day video, I think.
Really?
Sir? Yes, sir.
Okay. I mean, let me
Okay,
just check.
I will check mail again. Okay, sir, okay. Again, I will check in my mail and tell
Okay.
me through the messages.
Yeah, yeah. Just send me a
Okay, sir.
message. If it is not there, then I will send again. Okay. So
Okay, sir, okay.
your email is what? Which one? John.
They were John, Mike, I think. They were, sir.
Yeah, I'm looking.
Mm.
Oh, your name is not here, huh?
Mm. Sir, I registered and I also sent the mail ID through the WhatsApp the first day itself.
Okay, okay,
I
okay,
received
okay.
the link also. I received the link. Sir, I received the link also.
Yeah, they must have made some problem. Okay. Let let me send everything then, okay?
Okay,
This
sir.
is
Okay.
from our end, okay? The mistake is from our end, I think. Okay, I will look into it and I will send you all the videos, okay?
Okay, sir. Okay, sir.
Sorry for
Thank
the
you, sir.
inconvenience.
Okay, so no issue, sir. As
Okay.
well as send me the link for the software, the tools to be installed for all the tools. Mm.
Sure. I
Okay,
will
sir.
send you everything.
Okay, sir. Okay, sir. Thank you, sir.
Okay. Okay, see you tomorrow.
Thank you, sir. Thank you, sir.